Let's see, is the mic working? Can you all hear me? Perfect. Thanks for coming to my talk, Galaxy Brain, Type Dependence, and State Dependence in Property-Based Testing. I first have to give a bit of a disclaimer. I had high hopes in this talk that I would be able to incorporate the expanding brain meme and have it be like a really great metaphor, but it turns out I'm really bad at memes, so mostly there's just going to be a bunch of like galaxies and brains and stuff as images. So with that out of the way, who am I? I'm a type level member, so actually founding member. I'm sort of an errant maintainer. I've written a lot of Scala libraries and helped on them, but I've recently been kind of letting other people do a lot of the maintenance. So apologies if you've been waiting on me to publish releases for things. And I have this dual interest in expressiveness and performance of software. I think it's often easy to get one or the other of those, but it's often an interesting challenge to try and get both. And for my day job, I work on machine learning infrastructure at Stripe. If you're interested in talking to me about that work or possibly considering joining, of course, like everyone, Stripe is hiring. And you can go to my GitHub at the link right here to see some code I've worked on. As far as the talk, first of all, I'm really fortunate that yesterday Oscar and David introduced you all to both property-based testing and path-dependent types, since this talk will cover both. So hopefully I'll build on their talks or maybe muddy the waters a little bit. We'll sort of see. First, I'll give you a very quick overview of what property-based testing is. Then I'll go into some kind of complications and this particular motivating example that I found at work. We'll look at generating types to kind of solve this issue and test generic programs in general. Then we'll kind of look at tracking state during generation, which is another technique to deal with some problems we saw. And finally, we'll sort of review what we've talked about, and I'll try and kind of sum it up. Great, so now on with a very fast overview of property-based testing. So it's always worth noting the origins of this stuff. So this paper about QuickCheck in 2000 is kind of the origin story for a lot of property-based testing in functional languages. I encourage you to check it out. Much of it is still relevant to what we're doing today. But the basic idea, which I think we got yesterday, is you sort of describe how to generate input data that you want to do tests. Then you describe properties that should be true for all kinds of input data that you've generated. And then you can generate test cases until you're satisfied that things are correct or until you encounter a failure. A single failure signals that something about your assumptions is wrong. And this, if you think about it, this just generalizes the process of writing tests by hand. So to write a test by hand, you kind of imagine some input that would be valid. You kind of imagine what should happen based on that input, and then you write the test. This just sort of makes that process mechanical. Rather than you thinking of the test case, you teach the computer to think of the test case. And here's just an example I pulled from a project that I work on. This is Pages. I'm not so much interested in walking through exactly what the code does, but in Scala, a lot of property-based tests will have this form. So you'll sort of say, for these certain values of these types, I'm going to do this work, and then there'll be some assertion about what I think should be true. And if my assertion is wrong, then the test will fail. So this is just, if you haven't, show of hands, how many people have sort of done or seen property-based testing, besides at this conference? Pretty much everyone. Okay, great. So why is this great? The main reason, I think, is that we have a chance to catch bugs we didn't anticipate. If we anticipated a bug and wrote a unit test for it, that's not a case where property-based testing adds a ton, but where it adds a ton is that we often don't know where the bugs are really going to crop up. And anecdotally, this happens a lot. I think anyone who's done this can say that, yes, bugs have happened in places they really didn't expect. Certainly, I can say that. And I just want to maybe kind of formalize this idea in a weird way. So if you imagine the probability of catching a potential bug, that probability is equal to the probability of generating the input data that would demonstrate the bug times the probability of actually noticing that something went wrong with the input data. So if you kind of want an illustration, there's this kind of latent bug space, and then on one axis we have the sort of percentage that we generate, the percentage of input data that we generate in that space, and then on the other axis we have the sort of chance of noticing, and that kind of shows us the potential coverage we have, the chance that at some point our property will discover that we have a problem. Maybe not immediately, but at some point. And to me, this is the bigger you can make this kind of filled in box versus the latent bug space, the better off you're doing. So what does this mean? This means that obvious bugs tend to be caught immediately with property-based testing. Subtle bugs may actually only be found after months of testing. I've actually worked on libraries where bugs were exposed years later due to very, very subtle tests that just took a long time to actually notice the problem. So what does this imply, though, about how we should do property-based testing? Well, first, as Oscar kind of said yesterday, it means you should start simple. Just anything is better than nothing. So start with simple generators that at least give you some coverage of the space. And even those will catch real bugs. So it's worth just starting there. And then secondly, I think a lot of the examples we see are these kind of like, again, this reversing lists or these laws that are very kind of precise. Oftentimes, I think you just need to know that something went wrong. You don't have to even characterize it. So I encourage you to just look for like a signal that something went wrong. You don't have to actually find a root cause or a very specific, exact description of what happened. Just something seems fishy. As long as you can determine that, you can then kind of work backwards to figure out if there's a bug or not. Or maybe your test assumptions were wrong. Maybe the bug is in your test. But either way, you'll get some value there. So that's another thing I think that's worth taking. And then finally, that coverage matters. If you've done these first things, then the better your input data, the better chance you have, again, of catching bugs. If your input data is very limited in size, you won't catch bugs that require large input data. If your input data is only of a particular shape, you won't catch bugs of other shapes. And so once you've done those first two, improving the quality of your input data is likely going to help you catch more bugs. Just to sort of explain what I mean here, if the probability of generating the data that triggers a bug is 0, then your chance of catching it is also 0, no matter how good your assertions are, no matter how good your properties are. So you should prioritize 1 and 2, but once you've done that, I think prioritizing coverage will help. And this talk is actually about 3, so this is kind of why I bring it up. So anyway, that's my very, very quick high-level overview of property-based testing. I should add, by the way, if anyone has questions during the talk, please feel free to raise your hand. It's likely if you are confused, then other people will be as well, so I'm happy to stop and take questions at any time. But now on to the complications. And these are real issues that I hit at work. So this isn't just kind of an abstract idea. We had a system that we'd worked on for years that we thought was very, very rigorous, and when we used these techniques, we actually found 5 or 6 relatively serious bugs. So this is something that I'm kind of passionate about because I really think it adds value even when you're already doing a lot of testing and you're already trying to get everything right. So these examples are a little bit simplified for the talk, but I think the idea is very powerful and should be very transferable to lots of other similar projects. And I have kind of changed some of the names to gloss over what was actually going on. So first of all, for my examples, let's just get some terminology out of the way. So often people will talk about algebraic data types, or ADTs. Many of you have probably heard about this before. Here's some examples in Haskell. So we have a linked list parameterized on a type A, and then we have a tree that's not parameterized at all. That's always a tree of integers. And I'm not going to go into specifically what defines an algebraic data type. I just wanted to give you some examples. Often in Scala, you'll see these as a sealed trait with some classes that implement it. Those are often, like option would be an ADT, or list, or these sorts of things. And so what's a generalized algebraic data type? GADT. So basically, the sort of way that I like to think about it is ADTs often have recursive references. So in the case of list, the tail of the list is also a list. And if you have a list of A, the tail of that is also a list A. For a GADT, that doesn't have to be true. You might have a structure where there has a substructure of a different type. They're not aligned on a type parameter. But let's look at a more specific example. So how many people here have worked with shapeless at all in Scala? So like maybe a third, half. So shapelist has this type called HList, heterogeneous list. And I would say, list is an ADT. If you wanted to imagine what would list as a GADT look like, it would look like a shapelist HList. So in the shapeless case, the tail of your HList has a different type than the list itself does. In shapeless's case, it's just a sort of a strictly smaller type. It only has sort of the trailing, the Boolean and double types. But so I think that's like a very clear illustration of the ADT and the GADT. More generally, here's another example of a GADT. We've got some kind of expression GADT. We can multiply or add doubles, expressions of doubles, but we can actually build expressions of any type using the const class, and we can map expressions from one type to another type with a function from the input type to the output type using map here. So this would be an example of a GADT in that it's sort of a closed structure. You can't add new subclasses, and the sort of substructures are not guaranteed to be the same type as the parent structure. They can change and be polymorphic. Any questions about GADTs? Great, so then just to kind of go over in Scala some more GADTs you might be familiar with. So there's HList, which we talked about. In Scalding, there's Typepipe, which works with MapReduce. Spark has an RDD, which is kind of a GADT if you squint. FS2 has a stream, that's a GADT. The free monad in cat's data free, that's a GADT, and there's a whole bunch of these. So basically anything that has this kind of recursive structure that you can map over tends to be a GADT in Scala. And so I'm going to use Typepipe because I think it's a good example, and it's somewhat close to the problem we used at work. At work, we actually had a system that compiled either to Typepipes or RDDs or other platforms, but Typepipe exposes the same sorts of issues we had with our own kind of internal GADT. And Typepipe represents a MapReduce computation graph. It's lazy. When you build these things, they're not running immediately. You choose to execute them later. You should build up this typed graph. And if you've worked with FS2 streams or RDDs in Spark or other things, it's a similar kind of structure. So consider if we're going to write some tests in terms of Typepipe. So we would need a Typepipe generator. So this is the kind of structure I said a lot of property-based tests in Scala have. You have some for all statement and then some type. How might we generate Typepipes, like a Typepipe of string and int? What might we do? Well, these things are kind of sequences in a way, or streams. So one simple thing is just to generate a list and then transform that list into a Typepipe, which is what's happening here. And we can do this, and now we can write some properties using Typepipe. But there's kind of a problem. The problem is, actually, there's lots of ways to create Typepipes. The from constructor that we used here, Typepipe from, which takes a sequence, that's a way to go from a literal sequence, but actually often people are going to be mapping Typepipes or filtering them. They're going to be joining them with other Typepipes, doing various operations. And in theory, those Typepipes actually are qualitatively different. They're different graphs. They represent different computations that will happen on a MapReduce cluster. And our tests will never look at those graphs. So this approach won't actually exercise those types of graphs. And in many cases, the kind of bugs we're going to be interested in this talk are going to require particular shapes of graphs to be exposed. So let's imagine that we're actually the implementers of Typepipe. We're actually writing Typepipe, and we need to write tests not just that use Typepipe, but that actually are testing Typepipe itself. So we're like compiler authors for this graph that we're going to build up of operations. So we're testing the actual operations on Typepipe. We're not just using the Typepipe to test something else. We think that we might have introduced bugs in Typepipe and we need to catch them. So any two operations on Typepipes could have a bad interaction due to some error that we did or our colleague did or something. So we want to be able to generate these buggy graphs. This is kind of what I meant about you want sufficient coverage to catch your bugs. We want to generate all the different interactions, have some chance at least of generating those interactions so that we might notice a bug. And because we're going to be kind of optimizing the graphs, we need to have a chance to test those graph optimizations by creating the structures that then can be optimized. So some operations we're probably going to want to test are like mapping a Typepipe. We might want to filter, do a flatMap. We might want to call distinct. We might want to group Typepipes, which kind of says that they have some kind of key value structure. We might want to then join on those grouped Typepipes or convert back to a Typepipe from this group representation. So here's just like a small set. I think Scalding has something like 80 different operations in its kind of GADT hierarchy that in theory, if you'd probably want to test all of them, but for our purposes, we can just go with kind of this subset. Question?
These things you're seeing here, are those not operations of the Typepipe library itself, so are you then testing the Typepipe library itself?
Yeah, that's a good question. So the question is, aren't these operations actually in the Typepipe library? And indeed they are, but we're assuming that we are the maintainers of the Typepipe library. So we actually need to test this library. We're the authors of the library. We're pretending it for the purposes of my talk anyway. In theory, I don't think anyone here is actually a maintainer of Scalding, but if you are, this is probably not academic for you. So anyway, we're going to have some Typepipe generator, maybe called GenPipe, and ideally it's going to exercise all of these operations, or at least have some chance of exercising all of these operations. So again, here's kind of a cheat sheet in case you either haven't done this a lot or you want a reminder. So for the purposes of my talk, gen is the type that generates values. Sometimes you'll see this wrapped in arbitrary in Scala or in QuickCheck, but gen is the actual thing that powers that. So given some RNG state, we can get A values out. And cogen is sort of the reverse. Cogen takes A values and actually mutates RNG state, which ends up being kind of subtle, but we're not going to go into it in this talk. Basically, what's important is that, say if you want to generate a tuple, you need to generate the left, and you have generators for the left and right. You can smash them together, and now you have a tuple generator. By contrast, if you want to generate a function, which you can do, you need a cogen for the input type and a gen for the output type. And that's what you need to do to produce a generator for functions. And then we can use map, flatMap, and other sorts of combinators like that to transform our generators and build other types out of these generators. These examples are not actually using ScalaCheck. They're using kind of an idealized generator library, which I had been hoping to have public for this talk, but isn't. Hopefully will be soon. It's kind of a proof of concept. So anyway, going back to our previous generator, this is what we had started from before. We take a list, and we generate a type pipe from that. That's still pretty straightforward. It's pretty much the same as what we did. So we can kind of start there. That's kind of the base case for us. It's not recursive in any way. We want to generate a type pipe, so we generate just a list and feed it in. Using that previous generator, we can now define a type pipe generator that does filtering. So this basically takes the underlying type pipe generator and says, if you can build me type pipes, I know how to filter them. I'll build a predicate, an a Boolean function, and then I'll use that to filter whatever pipe I already generated. So as we can see here, we first generate a pipe, we generate a predicate, and then we apply that predicate to the pipe via the filter operation. So this would also return a gen type pipe. And you can kind of imagine our strategy is going to be build up a bunch of these different generators and then kind of combine them in some way and have a chance of running any of them kind of recursively. And that'll allow us to build up these graphs. So far, so good? Great, so now let's go to map. Map's kind of the next example after filter. So it looks pretty similar here. We're given two types, A and B. We're given a generator for the first type, A, and a way to generate functions from A to B. And we just do what you think. We generate a pipe first, then we generate a function, and then we apply that function to the pipe via map. So now we've built a type pipe of B out of a type pipe of A. So this does look good, but like I just have this we heard yesterday composition is very important. I think that's true. So let's kind of stop and see, do these things compose? So here's our sort of potential gen pipe implementation. We've got you can kind of ignore what this defer is doing here. It's not yet kind of clear why we're doing it, but this is using the gen from, the kind of simplest base case. And then here's adding in gen filter. So we've got gen from as one of our ways to build type pipes, and then gen filter is this other one. And now you can kind of see the reason we have this defer is that we have this lazy self value that we're actually using recursively in gen filter. So there's kind of this not being tied here. This is a little bit confusing if you haven't seen it before, but it's a pretty powerful technique, and say like Haskell kind of does this by default. In Scala, we have a little bit of noise to enable the laziness to make this work. But so this will either generate type pipes from a list, or it'll generate a type pipe and then filter it. And that type pipe might be itself filtered, or it might be from a list. And you can kind of imagine the kind of recursion going on. There's a chance here that we might just do a filter, 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 and then finally build from a list at the beginning. So we're going to generate these kind of combinations of filters and lists. So this still seems fine. It seems pretty composable right now. So now here's adding in map as well. So now we've got three ways to generate type pipes. We can go from a list like before, we can go from a filter, or we can go from a map. So as you see, we've got this generator from A to A. We apply that, and so this is kind of working. But something's a little fishy here. Do people agree that something's kind of fishy here? Maybe this isn't great? Yes, no, maybe so? Well, I claim that something is strange here. And the thing that's strange is that map actually goes from A to B. That's the map operation. That's kind of how we use map. But in this test, if we go back, we're always going from A to A. And why is that? It's because we need to apply this generator recursively, but the generator is always generating A. We don't have a good way in the context of this generator of introducing a different type, an underlying type for map to be going from. That's kind of a challenge here. We've very pragmatically chosen A to A because it kind of allows the types to line up, but it means that we're not really generating realistic maps. We're generating this kind of, we're always going between the same two types. So can we fix this? Is there a way to fix it? Well, sure, there's totally a way to fix it. We can sort of introduce kind of a hard-coded underlying type, a chance to go from int to A instead. And since we know int, we can actually use our gen pipe on int specifically to build this alternate kind of self to recurse on. And now when we go building our type pipe, we have a chance to go from A to A or to go from int to A. So now we are kind of exercising the polymorphism a little bit. So this does kind of work, but to me it feels like a hack. We're going to have to actually explicitly add every alternate type we want to check, and you can kind of see how this is going to be a little bit of a maintenance nightmare. Like every generator that wants to do this is going to have this same thing. It's not going to be very composable. It's not going to be very great. And actually, the combinatorics here are not really in our favor, because not only are we going to have like 80 operations, many of which have this character the same as map, but in fact, some of them have extra constraints that are going to be even harder to do this way. So for example, the distinct operation requires that you have an ordering for your type pipe. So unless we add an ordering constraint for all of our combinators, like for gen pipe and everything else, we won't have a good way of doing distinct, because we won't have proof that our A is ordered. Similarly with grouping, we not only need an ordering, but we actually kind of need this key value structure. It works on type pipes of tuples, not of any arbitrary type. So that's another challenge. Our trick we used for map won't really work for group. There's probably another trick we can use, but you can kind of see this approach is just going to fall down. Join kind of has a similar issue where the kind of input types and output types are different. You know, the inputs are not tupled, the output is, and so on. So these operations, a lot of them have these contours that are very difficult to express in the way that we've been writing the generator so far. Do people sort of agree with this? Are people not really convinced by this point? I think this is like kind of the motivation for a lot of what we're going to do next. So I think if people have doubts, kind of now is the time to give voice to them. No? Okay. Great. So then I sort of claim in this motivation section that writing recursive generator instances is already kind of hard, and recursive GADTs I think are significantly harder than other recursive generator instances, like for trees or lists or something where the type isn't changing. So we can kind of create wimpy generators that don't really exercise the polymorphism. That's one option. And that's actually a good place to start. I don't think there's anything wrong with doing that. I think that's a good place to start. But then eventually, you may find you want to go deeper and get more bugs. Similarly, we can sort of hard code some types and pray that that's good enough. Again, that's maybe a good incremental step, but it's still not really satisfying. And then you can kind of keep stacking these hacks on each other, but eventually I think that's going to become kind of unmaintainable or kind of a little bit of a disaster. So I think all these approaches do have major downsides, although maybe they're good starting points. So this is kind of the thing I'm most excited to talk to you about, this generating types idea. And this is the thing that builds on the path-dependent types that David showed us yesterday. So how do we kind of get around this problem that our generators, we're trying to test polymorphic combinators and polymorphic GADTs, but our generators are not really polymorphic in this way. So example-based testing uses hard-coded values, and property-based testing, we're generating the values, we're not hard-coding them, but we're still hard-coding the types in a way. And that's sort of the problem. That's why we're having such trouble, because we're saying upfront what the types have to be, but in fact, we kind of want more flexibility than that. So what if we didn't do that? What might that look like? Well, this slide doesn't really look like much, but this is it. This is the exciting thing that is going to solve all our problems. So if we just look at it in all its glory here, I don't know how, I guess I'll kind of go through. So this has a type member, sort of like David showed us yesterday. It has an abstract type member. We don't know specifically which type it is. We know there is a type. And then we have some evidence type constructor, and we know that we have evidence of whatever type we've got. That's what that evidence method tells us, that if we have a type with instance in hand, there's going to be some type associated with it. We don't know what it is, but we know that whatever that type is, we can get evidence parameterized on that same type out of it. And so here's kind of how you might see it in action. We have some type with ordering. We don't actually know. It could be int, could be string, could be like some complex type. It doesn't matter. But we can always pull an ordering out of it that's parameterized on whatever that type was. So you see that ordering of t0.type. That's saying that whatever t0 is, we know we can get an ordering of that type. And it doesn't have to be ordering. It could be gen. It could be anything that has this type constructor shape. That's a type constructor parameterized on one type. So gen has that structure. Ordering does. Cogen. All of these different instances do. And so here's kind of some of the machinery that we need to help use type with. So we have this aux type. This is really just a syntactic sugar. The thing on the right-hand side of aux is a valid Scala type, but it looks kind of funny, and it's sometimes awkward to write this in your code. So aux gives you a nice alias to express this in a more terse way. And then this apply method builds us type with values, basically. We say what the underlying type we're interested in, the type that's kind of hidden, that's A. And then the evidence type is the type that's going to be shown. That's going to be ordering or gen or something like that. And if we have an implicit evidence type parameterized on A, then we can construct this type with instance that kind of reifies the type as a value. And that's the question from Olaf. I'm sorry, can you repeat that? Yes, that's a typo. Apologies. Yeah, that should be. I think actually that probably better to name the implicit EVA, but yeah, I'll fix that before I post the slides. But yeah, that's exactly what's going on. And so this is the only way. And since this thing is sealed, the only way to build these values is through this apply method. And so we can see what using this apply method looks like. So these T0 through T2 are different sort of types reified as values that have ordering evidence associated with them, and we can put them all together in a vector. So this types value here is a vector of these things. And we kind of lost their underlying type. All we know is that they have this ordering, and I'm sort of demonstrating to you with this random shuffle that there's no funny business going on. We really are losing the type, and it doesn't really matter at this point which one we get out. We know that we have an ordering that's aligned with that T value, no matter which one it was. And that's what's exciting here, is that we can really talk about the type as if it was a value, and we can ignore the specific type we have. We just know that it exists. So this kind of proves that it really is path-dependent types that we're using. There's not some other trick here. The only way we can talk about the type is via this T path that we've got. So what happens when you need more than just an ordering? You need lots of evidence. So often we need both gen and cogen for our tests, and then sometimes we'll need ordering, we might need a class tag, we might need sort of an equiv or EQ type class. So there's a couple ways that we can do this, because in practice this is what we're going to do most of the time. So the kind of most straightforward that I've chosen to do here is create a case class that sort of takes all the different implicit evidence and wraps it all up together and provides that, and so says you can have this implicit testing value if all the underlying implicits are available. If not, then you can't have this. And so this allows us to kind of bundle all the different evidence we need into kind of one structure. So type with testing here kind of says, not only do you have a gen, you have a cogen, which are the kind of the two things you tend to need for testing. And you can kind of see here that we can extract either one of them out. So we can, once we have this type with object, we can get the gen, we can get the cogen, and we know that they're aligned with whatever that type is. We don't have to worry about that. Question?
Does the compiler complain about these two implicities? You can figure out?
No, I can figure them out because the context bound says that it has to be a gen A and a cogen A, so it'll figure it out. Yeah. And so then there's another way to do this, though, that's a little fancier. Maybe it's too fancy. I don't know. I haven't decided, but I figured I'd show you. So you can kind of build something that's like an H-list, but it's for evidence. It's implicitly available. This is kind of E-list is what I'm calling it, for evidence. And basically, this is the same idea. So we have this testing type alias that says you have a testing of A if you have a gen A and a cogen A and an ordering A and then enil. And so similarly as before, you can now talk about a type with testing, but instead of having to define the case class and define the kind of implicit constructor, you just kind of let the E-list handle that for you. And it's the same idea, only then you have to kind of destructure the evidence to get at the individual values. So this last line, the G is the gen, C is the cogen, O is the ordering. You can kind of destructure the evidence value to get those values. So I'm not really convinced that this is actually a better approach, but it's kind of nice in a way. So either way, this is exciting. We can now generate types. We can generate types without actually knowing what they are in advance. That's pretty exciting. I don't know if it surprises you that we can do this. It certainly surprised me when I first started doing this. So what does this look like? Well, this looks like basically we generate a bunch of these values and then we sample one of them. We choose one at random. So we say either I'll, oh geez, I got a typo here too. Oh, here we go. Well, this is the correct slide. So either we're going to get a unit or a Boolean or a byte or a character or a short or an int. And this list could go on and on. As many things as you want to define, you could generate one of them. So ideally, you would kind of define this in one place, and whenever you need to generate types, you could run this generator. And so I would argue that unlike before, this is extensible because we don't have to bake these types into every particular generator. We just have some type generator, and then whenever we need it, we can pull from it. You can have, however many or however few of these you need in your test program. So let's try and implement map now, map on Typepipe using this approach rather than the previous one. So as you can see here, there's no type parameters at all. We can just remove them. We actually don't need them. So basically the idea here is T1 is the kind of goal. This is the type we want to get to. We would like to get a typed pipe of whatever type T1 represents. That's what we want as the output. So how do we do that with map? Well, first we generate an input type dynamically. We sort of say, okay, we'll choose one of them. And then once we have that, we know that we can generate a Typepipe for that type. And next, we can generate a function from that input type to the output type using this kind of function combinator on gen. And then we just do the map. And so it all kind of composes the way you want. But the nice thing here is that we didn't bake any knowledge of the input types in. They're actually, GenPipe itself could be generating other types and then mapping those as well. There's no, it's not just like a single layer of mapping. We could have like multiple maps stacking up, and we wouldn't have to be aware of that here. So, question?
So the parameter type should be 0, right?
Where do you?
First line.
No, it's definitely.
Go from T1 to T1.
We go from T0 to T1.
So first line.
No, but this parameter is the output type we want. It's not the input type. So you see T0 is being generated. So the question was, normally when we write methods, we expect to see the input in the parameter list and the output on the other side. But in this case, we actually tell the generator what we want to end up at. We say, the place I want to end up is T1. And then you can figure out wherever you want to start is fine. As long as you get to T1 by some route, it's OK. So this is a great point to bring up, though. This is what's so powerful about this. We don't have to bake in knowledge of where we started in a term. We could actually start anywhere. So our type parameters are now path-dependent types. These are, T0 and T1 are legitimate paths, and that's what our types are. So we're leaning on this very heavily to make these generators very flexible. So if we put this together, you can see that we request some goal type. So T0 is our goal type in this case. So we're going to generate either gen from of T0, gen filter of T0, gen map, gen flatMap, and so on. And all of those can then recursively do whatever they want. So they can generate different pipes and map into this type. They can concatenate things. They can do whatever they want. So far, so good. But if you remember, I talked about there was an ordering constraint lurking. And so we haven't really shown how to do that yet. So the answer is you can actually, again, like I said, you can have multiple of these type generators. So let's, instead of just a testing class, let's have an ordered testing. So ordered testing gives you gen, cogen, and ordering. And then we can have a different universe of types that also are ordered. Not all types are ordered, but many of them are. And this will only contain those. Once we have that, we can actually have a different generator. So we have gen type, now we have gen ordered type, which is has the same as before, the same information as before, but also an ordering. And then using that, we can generate distinct combinators. So here at the top, we have our goal type, our T0, that has to be ordered. So we're saying, if you give me an ordered type, I can build you a type pipe of that used distinct to construct itself. So we build an underlying pipe of the same type, and then we use the ordering in evidence to distinct it. But you can also see at the bottom that if let's say that someone says, well, I really want you to use distinct to build your type pipe, but I also want you to end up at T1, and T1 isn't necessarily ordered. Well, we can still do that, because basically all we have to do is say, OK, well, I'll generate some other type that is ordered. I'll build a map of that type. I'll distinct that, and then I'll map back into the type you really wanted at the end. So we can use this technique to actually go between any types, even if there's constraints. We can kind of generate intermediate types that satisfy the constraints, and then map out of those types to the place that we actually wanted to get to at the end. So this is like a really powerful idea. This kind of means that I can say, give me a type pipe that has this final type, but I also want you to use these operators in the middle, and it's no problem. We can totally support that. So that's something that was very exciting to me when we sort of discovered we could do this. And the approach kind of is composable, because as you can see, we can kind of combine ordered testing and testing. So in the case of grouping, the key needs to be ordered, the value doesn't need to be ordered. So we can just take two different types, one that has an ordering constraint, one that doesn't, and sort of build up. We can actually compose these evidence. So we compose our generators, compose our cogens, and build up a new testing for this KV tuple. Then we generate pipes of that type, and then use the group combinator on it. So I hope you're convinced now that I can kind of turn the crank on this, that whatever constraints we have, whatever types we need, we can do it. We can build it, and so we can have we can actually exercise the full polymorphism of the type pipe computation graph just using this kind of generator strategy. So here's grouped, here's join using grouped now, and then here's kind of from join that kind of uses this mapping strategy. So we generate an underlying join and then map it back to some output type we care about. I'll kind of gloss over this because I think it's more of the same, but so again, what's really good about this approach? Well, it removes hard-coded types and kind of puts them in a different place that's kind of universally available and modular. And kind of like to the earlier point that came up, we often have a destination in mind, but we don't care about the route to get there. And in fact, we want varied roots. And so this kind of enables us to do that. We can make explicit the universe of types we're testing on. So for example, you might choose to exclude floating point types because they're kind of unstable and they're kind of unreliable for testing. Or you might choose to include them for that reason. You really want to ensure numerical stability. You actually want to be generating those types. Either approach is valid. It's kind of up to you whether you include them in your universe or not. The type generator itself could be pluggable, so I chose to kind of hard code calls to gen type, but you could actually pass that generator in, and then the person at the end of the line could actually decide what universe of types to run over. That's totally a good design. We can kind of control the distribution of types, which is, I didn't really show here, but you could imagine a frequency to say, I mostly want to generate simple types, but then every now and then I want really complex ones. And it's just really nice because parametric functions should work for any type, and we have a way of now expressing that. We can actually say, run this for any type, it doesn't matter. So it really closely models the original GADT definitions in the generators. What's less good? Well, it doesn't really play well with the existing kind of implicit driven approach that like ScalaCheck has, for example, with arbitrary. That just doesn't really work at all. And it requires a fair amount of setup. You probably noticed that there's like a lot of setup here. I think if a library came along that did this for you, it might not be too bad, but I think if you roll this yourself, there is a fair amount of setup. And it can also be a little bit hard to talk about the types. So everything's a path-dependent type now, so you will sometimes encounter situations where you have to clue Scala in to what you want the types to be because it's not going to infer them properly. And similarly, sometimes for comprehensions will not infer the correct types, and you need to kind of convert to like the explicit flatMap map structure. Yes, question?
How does error messages work with
Well, so I mean, I guess it depends. So you mean error messages like when you find a failing test case, or do you mean like when it fails to compile? So the question is, what do the error messages look like? I would say the compiler messages are usually not too bad. I mean, usually I think they give you the exact location, and often you'll see, like, you might see something where Scala says, I don't actually know what type, there'll be like a flatMap operation that says, I don't actually know what type to infer here. So that's a clue that you have to actually, it doesn't always want to infer these path-dependent types in some cases, so you have to kind of clue it in. The error messages during compilation are not so bad. The thing that is true, though, which maybe you didn't mean to ask, is when you generate these very big polymorphic graphs, sometimes diagnosing, like, I would say shrinking these things is not, at least in Scala, is not really a solved problem. I think probably there's stuff we could take from, like, the kind of modern, like, hedgehog and things like that to improve the way we do shrinking. But right now, you definitely get these big, hairy graphs, and I would say a different task is, like, finding a failure and then figuring out how to minimize it, and that's something that is still kind of non-trivial, but at least it lets you know that there is a bug and you need to invest time in hunting it down, which I think is still very valuable, even if it's not exactly where I want it to be as far as like shrinking to the smallest possible graph. Let's see, how are we doing? We're almost out of time. Okay, great. Well, so anyway, I guess the final thing I'll show you is this actually, there's a cool application of this for law testing as well. So how many of you have like worked with Cat's laws or other kinds of like discipline or other kinds of law testing? So maybe only a few. So maybe only a few of you will get excited, but I still think it's worth showing. So we can kind of generalize type width to kinds in a way if you kind of squint. So there's this evidence one trait that sort of says, if I have an ordering for A, I can build an ordering for some f of A. A lot of type classes have this kind of structure. And then we can talk about this testable one that kind of says, it's like our testable before, but instead of being parameterized on an A, it's actually parameterized on an F. And then we can have this kind of kind defined that's like, it's defined on type constructors, not on types. Otherwise, it's exactly the same. And then here's the functor identity law encoded in this way. So we say, here's some kind. It could be list. It could be, whatever type you're interested in. It could be like future, I guess, or ID. It doesn't really matter. And then here's the functor instance for it. And now I'll generate you test cases to test the law, and you won't actually know what the types I'm using are. Instead of right now we have to kind of hard code, we want to test on int or string or whatever. This just says, I'll just run it on anything. If you need, so we have some type A, and we're kind of proving to ourselves that we can apply the identity and get back the thing we started with. So this is pretty cool. But then the really cool one that's a little bit more intense is this composition law. So here we're generating 3 types, A, B, and C, and we're kind of proving to ourselves that we can basically, the mapping function is associative, that we can compose these mapping functions or we can just apply them in sequence and we get the same results. It's a little bit intense, but again, if you've worked with discipline and you've had to do this manually, it's just really cool not to have to juggle around like all these type parameters and all the weird different evidence they need. Instead, we can just have that kind of reified as values we generate. I find this really, really exciting. I think it's very likely that I'm going to try and build some library like this that we can use in CATS and other places. Let's see. So anyway, it was intense, but we tested the functor laws across potentially all types, and we control that universe, so we can actually expand it to add more types if we want. You could actually imagine combining this with a list of instances to test, to be able to test all your functor instances in one go. Just loop over the instances for each one, generate however many test cases you want, and bam, you've done all your functor testing in one place. There is some boilerplate, although I think with polish we could potentially remove some of it. And incidentally, kind polymorphism from Dottie would actually be really useful here, because that type 1 width is basically exactly the same as type width, only the kind is different. Instead of a type, it's got a type 1 that's a type constructor. So if we had a way of generalizing over those things, we could do this with arbitrary kinds, which would be really exciting.
Does your code compile with Delphi for the moment?
I tried an early version of this, and it did, but the most recent version I haven't tried. But I mean, yeah, I think as written, it should compile with Dottie. I'm not using any illegal type projections or things like that. Anyway, so yeah, I claim GenType's not a panacea, but it's really exciting. I had a whole different part of this talk about using state, but I think we're pretty much out of time here. So yeah, I hope this was exciting to you. I hope that I think this approach does generalize to other languages somewhat. I don't exactly know how you'd encode it in Haskell, but I'm pretty confident there's a way to do it somehow. And I just think it's a really useful way of thinking about this, and actually lifting types or reifying types as values, working with them there, actually gives us a lot of interesting flexibility that we wouldn't otherwise have. So thanks, and I'd be happy to talk after this. I don't know if we have time for questions or not.
Yes, two questions. How does this affect compiler speed, the default Scala compiler, and is it possible to use, for instance, the reasonable Scala compiler to do stuff like this?
So there's two questions. The first is, how does it affect compile times? Honestly, I haven't really noticed a difference. I think if you made really heavy use of that kind of shapeless evidence list, it's possible that could be slow, but everything else it's really no different from normal property-based tests. So the second question is about using reasonable Scala compiler. I haven't tried that. I don't really know. I don't actually know what the limitations there are, so I'd be happy to look into it, but I just don't know. Yes?
Yeah, so you mentioned this was taken from your work, but simplifies it, and that you had found a number of serious bugs.
Yeah.
Benefit from
Sure. Yeah, so one type of testing we do, because we have these different platforms we compile to, one of which is Scalding, one of which is Spark, there's like a real-time platform that uses Kafka and so on. One of the best tests we do is not only we generate random graphs, we generate random input data that corresponds to the random graphs for like event sources. And then we can actually push the event data through multiple different implementations and see if they agree. So we can run, there's an in-memory interpreter that's very slow, but relatively simple to understand. There's Scalding, there's Spark, there's real-time. We can test all of them against each other, and if we notice any discrepancy, that means there's a bug somewhere. So basically doing this, we caught several discrepancies between our platforms, and one of the promises we make is that all the platforms will evaluate the same. So this is like a very important kind of bug for us to catch. This is kind of like a type of oracle testing, really. And so that, in our case, there's a lot of complicated joins we support, where like complicated join logic, and basically there's situations where we're pushing events through doing these joins, and there's like a lot of places where either the ordering can get messed up or different things can interact in a weird way, and those were the types of bugs we tended to catch, where you only got them through these very complex graphs. In other words, simple graphs would be fine. It was just when you had these very nested interactions, it would expose certain bugs. And so that was where I thought the value here came from, is that previously it was very hard for us to generate interesting graphs to work on, and now it was very easy, and so we suddenly exposed this whole new class of bugs that we were never seeing before.
And would you say that being able to go from A to B, B to C, C to A again, does that expose more bugs than just
So the question is, did being able to go between the types expose more bugs? To some degree, I mean, one thing that it did help with is we have a lot of these serialization instances because we need to serialize some of these boundaries, and so being able to if you get serialization wrong, but you're always using the same type, things kind of work out. If everything is the same type, then you might actually be using the wrong codec to deserialize, but it actually works out because the codecs are all the same. So I think we had at least one bug like that. In other cases, though, I would say it was less about the fact that we were generating these different types, and more that some graphs were very difficult to generate because the subgraph was only valid for certain types that we couldn't represent. So it was more that we we had a hard time generating these complex graphs because the polymorphism meant that we couldn't generate the realistic types to get them to a lineup, so we were just leaving out certain cases that were difficult to represent, if that makes sense. Any other questions? Well, I'd be happy to talk more if you have questions later, but again, thank you.